let's say we have the double integral from 0 to 1 of the integral from e to the y to 1 of x squared divided by the natural log of x minus 1 dx dy. Oops, can you see that? Oh, there's already a chat. Let's see what's in the chat. Could you go over number 13 for double integrals? I'm not. Let's see. Maybe I might have that one. Let me double check. I was just looking at my stuff. Thought I had. Sorry, Amy. I've always got a bajillion papers everywhere. Well, we'll explore that after we look at this one. So, if you look at this, you might notice that that thing you're trying to integrate looks challenging. I have no clue how you integrate x squared over natural log of x minus 1. If it doesn't look recognizable or like there's a good choice for a use of or use of my parts, it's probably a good clue that we should be changing the order of integration. Now this one has, this is the pretty much the way the person wrote the problem to me. And I was going to fix it, but I feel like we should, because I think there's an issue with it that was on accident, but we're going to look at it anyway. So let's try drawing the region. I'm not good at drawing x equals e to the y. For me to draw that, I'd really rather just solve for y. So we take the natural log of both sides. We get the natural log of x equal to y, which I'm perfectly good at drawing. That just looks like your usual natural log function, which has an intercept at 1, 0. And then my upper limit of integration, I shouldn't say upper and lower, I should really say left and right, right? Because it's x equals a left thing to x equals a right thing. So my right limit of integration is x equal to 1. And now things are about to become problematic. So the problem here is, if we're going from left to right, this is the left and this is the right. So I should do something like this, but don't draw that. Because the problem here is my y values are going from 0 to 1. So I'm really from here to say, like, maybe here's y equal to 1. So I have to be between y equals 0 and y equals 1, but my functions are kind of out of order because my left one should be y, my right one should be 1. I don't think normally you'd be written this way, but if it was for some reason, here's how I would fix it. I would fix this by changing the order of integration here. I don't think this is something you would typically have to do, but since the problem was written this way, I'm just saying, like, if you happen to see something like that, this is how you could fix it. If you know that the thing you're looking at has things kind of backwards, rewrite it as the negative integral from 0 to 1 of the integral from 1 to e to the y of x squared over the natural log of x minus 1 dx dy. It's totally fine to change the order of integration for one of your limits and bring that negative out in front, or to tack on an extra negative. Still the same thing. And now this makes way more sense to me. My left boundary is x equals 1. My right boundary is x equals e to the y. So here's my horizontal strip I would have drawn for the way the integral is currently set up. And then my strips go as low as 0, as high as 1. Cool. My region is just that little, not quite a triangle, but kind of triangular looking thing. This point here is the point 1, 1. This point over here, well, again, if this is y equal to the natural log of x, or x equal to e to the y, if the y value is 1, then the x value has to be e to the 1, which is just e. So the coordinate there is e, 1. It's not super necessary to find these coordinates, but it does help if you're trying to rearrange how you're going to write the order of integration. It's usually not a bad idea to find them. So now we're going to try and rewrite this thing. Let's zoom in just a little bit here so hopefully everyone can see that decently. So I'm going to try and I'm actually not going to redraw it. I'm just going to reimagine what I'm doing. So instead of a horizontal strip, I'm going to have a vertical strip. And a vertical strip has an upper limit of y equal to 1 and a lower limit of y equal to natural log of x, or the top and bottom of my rectangle, the ends of my rectangle. So now my new integral, not the pen I want. There we go. My new integral still negative, but now instead of from x equals 1 to x equals e to the y and y equals 0 to 1, we're going to go from y equals natural log of x to y equals 1 on our inner integral. And from x equals 1 to x equals e on our outer integral. That's going to be a dy dx, still the same function that you are taking the antiderivative of. Yeah, oh, sorry. Yes, anytime, please. Just say, James, and we can't see the thing. Okay.
Well, I think my question is like, when specifically do you know that even you like you're looking at that bottom portion and the top portion to figure out the order of it, you know, like
when you like, you mean the region I've shaded here versus like this region over here? So it really is based on the original boundary. So, and I will fully admit, the way this original function was written, it is not super duper clear. But I know that so basically from this integral, I know that the x has to be between the function x equals e to the y and between the function x equals 1. So it could have been between here and here, or it could have been between here and here, right? It could have gone this way or that way. But what determined which part I needed was also the fact that the y values were from 0 to 1. So I have to be from y equals 0 to y equals 1. I can't be down there because y doesn't go negative. I would say generally when you're doing this, it's always drawing the inner limits of integration as functions. So drawing the entire y x equals e to the y and x equals 1, right? Drawing those graphs and then trying to find the region based on how high or low you are here, or if you're changing it, how left or right you are. We'll do one more just to kind of talk more about it, but because again, this example is not primo. Yeah.
so like so the one is a straight line, right?
Which one?
Well, like x equals 1.
That is this vertical. So this vertical line is x equals 1.
Yeah, so that goes to the ln function, right? But it equals the y function.
When you say goes to, what do you mean?
So you go from left to right.
Correct. And so again, what I should say about this example is this is not a good example because it has had the things out of order in the first place. So you're right. Normally we go from left to right here, but the problem is we're in a y region where the left function is actually x equals 1 and the right function is actually y equals natural log of x or x equals e to the y. So this one is kind of atypical.
It's atypical, but is it incorrect? Like my question is like, if it's supposed to be like to the left to right, isn't that incorrect?
It's not, well, it's not incorrect. It's just we have to reimagine what's going on. So the thing here is that I can't be down here because down here is like, say, y equals -2 to y equals 0. That region right there, I don't get that because my y values are between 0 and 1. I have no choice. I don't get to be down there. But I have to be between these two functions here. So I'm going to have to rewrite what's the left one, what's the right one. And the way I did that was by changing the order of integration by attacking on a negative sign. That's how I fixed this one. Normally, you should not have to do that.
Okay, so like, you like your function problem, like you check it out and then you like, oh.
Right. Normally, I would have drawn this one, and I would have thought I was down here as well because I was like, oh yeah, from left to right. But then I would have noticed that my y values are from 0 to 1. I'm like, that's the problem. But yeah, you're right. This is probably definitely a less than normal problem.
I think the problem is specifying to look within the book for the
Oh, okay. That would help, sure, if we were to look in the first quadrant. Okay. Awesome. Sure. So looking at this here, I'm now trying to use a vertical strip. So meaning, instead of from a left x equals something to a right x equals something, now I'm going from a bottom y equals something to a top y equals something. Basically, I'm looking at the ends of my rectangle. When it's a horizontal rectangle, I'm going from left to right. When it's a vertical rectangle, which is what we do if we want to change the order, so we change the orientation of a rectangle. I'm looking at a vertical rectangle, I go from bottom to top. The rectangle, the bottom of the rectangle is touching the function y equals natural log of x. The top of the rectangle is touching the function y equals 1. And then after that, we kind of just ask how far left and how far right can we go? Well, this rectangle can go as far left as x equals 1 and as far right as this x value here, which is x equal to e. That's how we're getting those boundaries. And if it helps, and I really think it does help, I would write that in here, meaning I would write y equals natural log of x, y equals 1, x equals 1, x equals e. I find that super helpful personally. That's honestly, that is usually the hardest part of these problems, is if you have to rearrange them. The rest of this one shouldn't be too bad, but let's do it anyway. So we got a negative integral from 1 to e. And to differentiate this with respect to y, well, since there aren't any y's in there, you just multiply the whole thing by y. So I've got my constant x squared over the natural log of x minus 1 times y, where y is going to be evaluated from y equals natural log of x to y equals 1. I often like to put that in its own inner parentheses. We integrate here. I would just think of the x squared over natural log of x minus 1 being factored out. You have a negative integral from 1 to e, and you've got x squared over the natural log of x minus 1 times 1 minus natural log of x. Plugging 1, subtract, plugging natural log of x. And here's what happens. Well, you can see this in one of two ways. You can either see that 1 minus natural log of x divided by natural log of x minus 1 is going to be interesting. They'll cancel out and leave a negative 1 behind if you like. Or you could actually distribute this negative 1 here to that term over there and say that you have negative 1 times 1 is a negative 1. Oops. Oh, geez, James, come on. From 1 to e with x squared over natural log of x minus 1. And then this is going to become negative 1 times 1, negative 1 times negative natural log of x. And the negative 1 plus natural log of x there and the natural log of x minus 1 there do actually cancel out. Just super convenient. Otherwise, we couldn't really do this. So again, I'm distributing I'm multiplying the negative 1 into the integral, but I'm picking which factor to multiply it by. I could have multiplied by the x squared. I could have multiplied by the bottom here, or I could have multiplied by this factor here. I decided to multiply by that factor there, so that it ended up looking like the denominator. And so then they cancel out. So then we're left with the integral from 1 to e of x squared, and that's not terrible at all. That's x cubed over 3 from 1 to e. That's just going to be e cubed over 3 minus 1 over 3. We definitely do have to do this simplification, though, to be able to integrate it. Otherwise, it just can't be done. Oh, you know what? Someone asked about 13, but I think that's from the double integral section, which I don't think they have. Do I have on me? Yeah, I do. Yeah, okay. The last one. Okay. Oh, yeah, I've seen this problem. I've helped a few people with this problem. Yeah.
How would you just start approaching the problem of this? Like, in terms of the graph, values that you're giving?
Yes, but I graph the inner ones first. So let me show you. Let me just make up something semi-random here. Let's say we have this double integral. We have the double integral from y equals x squared to y equals. Let's be careful here, James. It's always problem is picking nice things here. Sorry. Y equals x plus 2. Yeah, that works. So y equals x plus 2. And then the x values are going to be from x equals -1 to x equals 2. dy dx. Let's say we were trying to rewrite that one. So step 1 is to graph the inner functions. So step 1, graph the inner limits of integration. You guys' second test is still not for a while, right? It's like the 29th, I think. Yeah, okay, so we got time. I think it's basically everything up until chapter 12 is second, right? We're gonna cover chapter 11, have your second exam, and then after that will be chapter 12 for like a week, right? Because like there's really not a lot of class time in December. So first we graph the inner limits of integration. So I'm gonna graph. And actually, I would just go ahead and graph them because I know what they look like already. But to get a better graph, it's probably a good idea to find where they intersect each other. Now, it's not a bad bet that they intersect each other when x equals -1 and x equals +2. If you plug in 2, 2 plus 2 is 4, 2 squared is 4. Oh, great, they intersect there. Plug in -1, -1 squared is 1, -1 plus 2 is 1. So a lot of the times, those 2 points are where things intersect. Not always, not always. Or you can set them equal to each other and solve it, right? X squared equal to x plus 2, x squared minus x minus 2 equals 0, factor. And oh yeah, you're going to get x equal to +2 and x equal to -1. The parabola y equal to x plus 2, or the parabola y equal to x squared, let's say that right. You know, has your usual parabola look. It looks like this. I usually just kind of throw these 4 or 5 points on the parabola pretty easily. And again, your picture doesn't have to be perfect. And then y equals x plus 2 goes to the point -1, 1, and to the point +2, 4. So it looks something like that. And you don't need to, but I like to draw my vertical strip just to be like, oh yeah, that's what I was doing. I was going from a low of y equals x squared to a high of y equals x plus 2, from as far left as x equals -1 to as far right as x equals 2. Now, if I'm going to change it, I'm going to have to change it to a horizontal strip, which is going to be extra terrible because I'm going to need 2 intervals. Because below y equal to 1, my horizontal strip has the parabola as both the left and the right function, whereas above y equals 1, my horizontal strip has the left function being this blue line and the right function being the parabola. Okay, it's not that terrible though. So if we were going to do this, let's do the top part first. So the top part, meaning this part here, which I'm going to shade in like this, we do have to solve the functions for the other variable, right? Instead of writing y equals x squared and y equals x plus 2, this blue line, we should solve for x and get x equals y minus 2. The parabola is a little extra tricky in my opinion. If I take y equals x squared and solve for x, I'm going to get x equal to plus or minus the square root of y. The right side of the parabola is x equal to the positive square root of y. The left side of the parabola is x equal to the negative square root of y. And then we do the thing. So I'm always going to work from the inside out. So I'm going to write the inner limits of integration first. Inner limits of integration first. So for this top half, that's going to be, well, let's see. So my horizontal rectangle is going from left to right. So the left boundary is x equals y minus 2. The right boundary is x equals this positive square root of y. And that's going to be a dx because it's what x is equal to. And then my outer limits are just how low and how high we go. So this horizontal strip goes as low as y equals 1. I feel like I said something wrong there. No, I didn't. I'm just messing myself up. And as high as y equals 4, I believe. That's the point 2, 4. I really can't stress enough. I find it super helpful to write what things are, meaning I think it's really helpful to say this is x equal to y minus 2 and x equal to root y. So that then you don't confuse yourself like I just did when you're saying, oh, this is y equals 1, but I've got a y over here. That was confusing me. So that's right. But now I'm like, oh yeah, this is what x equals. This is what y equals. I think it's perfectly good to write those in there.
I understand how you got x equals and x equals, but why is it 1 not 0?
Well, because if I go below 1, I've got a different rectangle, right? My left boundary is no longer the line when I go below 1. Because these points, this point of intersection here is the point -1, 1. So when the y values are lower than 1, my left boundary is no longer that line. Are you cool with how we got y equal to 4 as the upper boundary? It's okay if you're not. Okay, so we're looking for this point of intersection, which is 2, 4. So what we're really saying is that anywhere in this picture here, I can draw a horizontal strip whose right boundary is the parabola, whose left boundary is the line. And I can go as high as all the way up to y equal to 4. Now, when I go up to y equal to be close to 4, the length of my strip isn't very long, because if y is like, say, I don't know, 3.9, 3.9 minus 2 is 1.9, and the square root of 3.9 is a little bit bigger than 1.9. There's not a lot of distance between them. So I'm getting a very, very small strip, but I can still get a strip all the way up to y equals 4, all the way down to y. And when y equals 1, my strip is going all the way from a value of -1 to a value of +1. So my strip has a length of 2 when I'm down at the bottom. But I'm just trying to say, in general, my strip length is the right function minus left function, and I can have strips all the way as low as y equals 1, all the way as high as y equals 4. The easier way of saying it is just look at your boundaries of your region, right? So if these inner parts are x equals, then these boundaries have to be y values. It's a really a look at the picture kind of thing. Like there's not a better way to do it than drawing the picture. Let's look at the other half. So the bottom part. So same idea, but now the left-hand boundary is going to change. So for the left-hand boundary, we're going to have x equal to the negative square root of y. For the right-hand boundary, we're going to have x equal to the positive square root of y with a dx. And then this region here, the y values go as low as 0, as high as 1. And we would add those two intervals together to get the actual total area. And it would be area because my integrand was just 1. No, never. Good question. The answer is never. Yeah. One other thing that's nice to know is if both the outer bounds and the inner bounds are just constants, then your region is a rectangle. And then, which means you can switch them without doing any work. It's nice. It also means that if you're finding the area of that region, like if you're calculating average value, the area of that region is really easy because it's literally just the length of this side times the length of this side, which is the area of the rectangle. Saw a hand over here. Yeah.
Yeah, that question was just because if it's a rectangle, they're all constant.
Right.
So you don't need
Exactly. Right. And if it's not a rectangle, they can't all be constants. So if you have a region that is not rectangular, which is pretty typical, the inner limits of integration have to have a variable showing up in at least one spot. There is no way you cannot have that. Cool. Let's look at that problem 13 from the double integration section. Okay. So let me move. Sorry, I feel like we're all over the place here. Oh, nope, other way. Sorry. Okay, so let's see here. My version of this is find, can you see that? Almost. Find the volume of the solid. Region, I feel like is not the word. I don't think you need the word region here. I'm just gonna get solid. It's fine, it's just English. Bounded above by z equal to 9x squared plus 8y squared, and below by the triangle enclosed by the lines y equals 7x, x equals 0, x plus y equals 8. And for graphing purposes, I would totally rewrite this as y equal to 8 minus x, just because that's how it's easier for me to graph anything as y as a function of x in the xy plane. So it's kind of like you have like a triangular pillar, but the top is kind of like a curvy surface. If that makes sense. Like any of the buildings you might see in San Francisco, right? The base is some sort of rectangle, square, maybe a triangle, and then the top is often kind of sloped in some interesting, fun looking way, some architectural way. I'm not going to draw the surface because I can't. Can't probably too strong a word, because it is challenging for me to make it look good. but I definitely can and will draw the region. And you should all draw the region of integration. So I've got y equals 7x. I'm not going to draw it too steep. I've got y equals 8 minus x. So that's going to be something like that. I could label my points of intersection, or my x and y intercepts. That's the point 8, 0. It's the point 0, 8. I should find where they intersect each other. If I set 8 minus x equal to 7x, I get 8 equal to 8x, or x equal to 1, and y equal to 7. And now the important question here, and this is the place where it's really, really easy to do the wrong thing. Which triangle are we talking about? That one there or that one there? The top one, the left one, or the bottom one? The left one. How do we know? Because the left one is the one that has all 3 of these lines as boundaries. Both y equals 7x, y equals 8 minus x, and x equals 0, which is the y-axis. So that is our region that we're looking at. Be careful. It's easy to mix up which axis you've got and accidentally grab the wrong triangle there. So just be extra, extra careful there. I'll say that in a minute. Then we get to make a choice. And here there is definitely, I won't say there's a wrong choice, but there is a worse choice and a better choice. And the better choice here is to use what kind of rectangle? Horizontal or vertical? Vertical. Why is horizontal a worse choice? Well, the same reason it wasn't a great choice in the problem we just did. Because if I used a horizontal rectangle, halfway through the thing, I'd have to use a different limits of integration for my left to right deal. So you always want to draw the rectangle that no matter how far you slide it, so if the vertical rectangle, no matter how far I slide it left or right, the top function is always that, the bottom function is always that. If it was a horizontal rectangle, I would say, okay, if I slide it up and down, is the left function always this? Well, yes. Is the right function always that? Well, no, it's not. Because if I slide it down too far, I'm going to get that as the right function. So you always want to pick the one that you can slide and not have to change the function. Sometimes it's impossible to avoid. Typically not in this class, though. So usually you can always make the better choice. All right. So we're going to write that the volume is the double integral of our function. We'll see about finishing this problem because it's kind of gross. 9y squared. And then we want our inner limits of integration. All right, you guys write the inner limits of integration. Right what the bottom thing should be and the top thing should be. I'll give you a minute. I want you to write those things right there. And then if you're done with that, you can do the other part too. Okay. I should have labeled my lines here. You have to make that choice. Well, it's not really a choice anymore. You have to determine which way it should be based on which choice we have made here. I picked a vertical rectangle. That means we are set in stone which way we are doing the dy dx or the dx dy. That is correct. Because our lower boundary here is y equal to 7x. Our upper boundary here is y equal to 8 minus x. Again, that's why I really like to write the y equals part. It helps me know what's going on, which is why I don't write the dy dx until after I've done my limits of integration. I'm going to write y equals, and be like, oh, dy. And then I'm going to do x equals 0 to x equals 1. I want to point out, and this is important. If we had done it the wrong way and grabbed this region here, we wouldn't have gotten x equals 0 as one of the limits of integration, which would have been problematic since it is one of the boundaries. So that's also something to pay attention to. If you're getting limits of integration that don't have one of the actual, like x equals constant or y equals constant that is a boundary, that's sometimes a good indication that you made the wrong choice. It's not like 100% always going to work that way, but it's good to look for. All right, the rest of this is just pure trash. So we'll talk about this. We're probably not going to get a super nice answer. I'll remind you that web work does take unsimplified answers. So once you get to the integral and you plug in your stuff, You might just like leave it as a bunch of terrible fractions added together and type that in instead of trying to make a nice single thing. Okay, it definitely helped someone struggle through it. And there were a lot of tiny errors we made that like we had to keep finding, and it would have been much easier for both of us if we just typed in the original thing, which we had right, but then we were simplifying it wrong along the way. So just a word of warning. Let's see, integrating this with respect to y first, we're going to get 9x squared times y plus 8y cubed over 3. From y equals 7x to y equals 8 minus x. It would have been nice if that had been a 9y cubed instead of an 8y, or sorry, a 9y squared instead of an 8y squared, but it's not, so such is life. Plug in, you're going to get the integral from 0 to 1 of 9x squared times 8 minus x plus 8 times 8 minus x cubed over 3 minus 9x squared times 7x. And instead of doing a minus the parentheses with a plus, I'm just going to do minus minus, right? Because it would be a minus sign if I distributed it. 8 times 7x cubed over 3. And that is pretty terrible. Yeah, pretty terrible. Here's what I would do. Here's the simplification I would make. Oh, God, yeah. So I would multiply this part out and get the integral from 0 to 1. 9 times 8 is 72 x squared. 9x squared minus x is 9x cubed. And I'm actually not going to multiply this part out here. This 8 minus x cubed, although it does multiply out into 4 awful pieces, we can integrate 8 minus x cubed pretty easily. It's going to be 8 minus x to the 4th divided by 4, also divided by a minus 1 because of the minus x right there. It's like a mini u substitution. So we'll just leave that as is because we haven't integrated it yet. I would multiply this part out. 9 times 7 is 63 x cubed. And I was kind of intrigued. The person I was helping actually didn't multiply this part out, which I found a little challenging, but I think is worth doing it that way because I don't want to get 343 times 8. So we're just going to leave that as is, and we'll talk about how that works. It's also going to be a mini u substitution. Of course, this is the moment I've ran out of room on this page, so let's go to the next page. Okay, and let's not bother combining like terms, even though normally one would, because there's just so much to keep track of here. So let's see what we've got here. So let's write the integral again so we don't lose it. This would be an ideal moment to combine like terms if I had decided to do that, which I should have, but I didn't. So, you know. The only terms you could have really combined were the negative 63x cubed and the negative 9x cubed, but still. Cool. So now let's integrate. So we're going to get 72x cubed over 3. 72 is divisible by 3. It is 24. So let's write 24x cubed minus 9x to the 4th over 4 plus, okay, here is one of the fun ones. We're going to get 8 minus x to the 4th over 4, and then also divided by a negative 1. Because when you anti-differentiate something where you would have multiplied by a constant for the derivative, you divide by that constant. It's like integrating cosine of 6x and getting sine of 6x divided by 6. Same idea here. Does anyone want me to say more about that? I'm happy to. Okay. Keep moving on. 63x to the 4th over 4 minus 8/3. Okay, same idea applies here. If I anti-differentiate 7x to the 3rd, I'm going to get 7x to the 4th divided by 4. What else do I have to divide by? A 7. Let me point out how that would have worked if we hadn't done it that way. If you just multiply this out, this part right here is equal to 8/3 times 7 cubed times x to the 3rd. That's a constant. And if you anti-differentiate that, the constant hangs out 8/3 times 7 cubed times x to the 4th over 4. That's exactly what we're getting here. 8/3, 7 to the 4th divided by 7 is 7 to the 3rd, and x to the 4th over 4 is what we have. So it is the same thing, just a different way of seeing it. It's gross either way. Oh, and I shouldn't have written DX. That's terrible. Should be evaluated from 0 to 1. Question.
Could you make it easier and just combine the negative 9x and the negative 6?
I could have, yeah. I probably, yeah, I should have, but I didn't. But you're right, because 9, so negative 9 minus 63 is negative 72. 72 divided by 2 is 36. 36 divided by 2 is 18. So yeah, so that works out relatively nicely. So we could have, let's go ahead and make that this part and this part here come together and make a negative 18.
So on the test,
Yeah, totally. Yeah, it would be hard for, I don't want to say that. I would be surprised to see a question like this on an exam with such terrible stuff at the end, but I've seen lots of surprising things, so, you know. Anyway, plugging in, this is where things are relatively nice at the end. You plug in 1, you just get all the coefficients. You plug in 0, you just get a bunch of zeros. So plugging in 1 and getting the coefficients, we're going to get 24 minus 9/4 plus, be careful here, 8/3 times 8 minus 1 is 7. Ooh, we have to be extra. We'll be a little more careful than I was going to be. So we get 7 to the 4th over a negative 4 minus 63 over 4 minus 8 over 3 times 7 to the 4th over 4 times 7. And we actually do have to, so this is one of those problems where you do have to be careful when you plug in 0. Most of the things when I plug in 0, I'm going to get 0. 0, 0, not 0. I'm going to get 8/3 times 8 to the 4th over negative 4. 0, 0. So there is one thing that isn't 0 there that you have to look out for. And I would leave it like that. I would type, okay, that's a lie. I would mostly leave it like that. I would probably rewrite this as a negative 9/4 and negative 63/4 was negative 72/4, which is negative 18. So I'd probably write this as 24 minus 18 plus, I'd probably simplify this as negative 2/3 times 7 to the 4th. It dealt with that. Minus 8. This is terrible. Who assigns a problem like this? Sorry, that's not fair. I probably write this as 2/3 times 7 to the 3rd. And then minus, cancel an 8 there, or 4 there and 4 there. So plus 2 over 3 times 8 to the 4th. It's terrible. There's probably more simplifying you could do. Like that's obviously 6. You could probably factor out like a negative 2/3, 7 to the 3rd here, and make that a little easier, but I don't think you need to. I don't think it's worth the effort, right? I'm not trying to test you. I know I didn't assign homework on your ability to do this algebra or this arithmetic, but if you want to do it, you should. I just don't think if you have a lot of free time, you should do this. If you don't. All right, let's move on to the other stuff. The systems of linear differential equations. Oh yeah, question. Yes, this one right here, sure. So if I was integrating 7x to the 3rd, and I didn't want to just multiply it out, though I totally could. I could do a u sub. U equals 7x, du equals 7 dx, 1/7 du equals dx. I could rewrite this as the integral of u cubed times 1/7 du. And that's going to end up being u to the 4th over 4, and then also a 7 plus c. And then the u is equal to 7x, so I get 7x to the 4th divided by 4 times 7. So extra 7 in the denominator is coming from the fact that we were doing a u substitution. We just weren't showing the work for it.
Wait, so why couldn't you do it like the way?
I'm saying you could. You could totally, right? And I did over here, right? You could also have just said, oh yeah, that's the integral of 7 cubed times x cubed. 7 cubed is a constant, and you're getting 7 cubed times x to the 4th over 4, which is exactly the same as this. It just looks different. Right? Here you've got 7 cubed over 4. Here you've got 7 to the 4th over 7 times 4, and one of those 7s cancels, and you get 7 cubed over 4. So these really are the same. They just look different. But the reason I was kind of pointing it out here is because you didn't really have to do it here, but it really made more sense to do this one that way. So I kind of wanted to show the similarity. But just like here, when you integrate 8 minus x to the 3rd, and you get 8 minus x to the 4th divided by 4, and also a -1, because -1 is the coefficient of x here. Just like here, you get a 7x to the 4th over 4, and then you also have a 7 down there because 7 is the coefficient of x there. That's right. Cool. What time is it? Okay. All right. Oh, wow. That was interesting. Okay. Back to the others. Back to the chapter 11 stuff. So systems of linear. We'll get to the nonlinear eventually, but we gotta deal with the linear stuff first. I was gonna look at one thing real quick here. Pretty sure I feel like, oh yeah. It seems to me, with looking at a quick inspection of your, yeah, that for all these systems of linear differential equations, just as a reminder, our systems, at least at a quick glance, our systems are all homogeneous. Which just means there isn't like an extra constant in the way. They're all being set equal to 0, and you're getting x1 and x2 equal to 0. So what this really means for us, this essentially means that our equilibrium is always going to be the origin. For example, we want to solve the system dx1 dt equal to 3x1 plus 5x2 dx2 dt equal to, yeah, sure, let's go that way, -x1 plus x2. We'll solve, we'll also classify. So let's go ahead and do it. When someone says solve a system of linear differential equations, the way the first things you should do are find the eigenvalues and the eigenvectors. So that's always kind of up first. If you're asked to solve, if you're asked to classify, well, even then you still find the eigenvalues. So no matter what, typically the first thing you should do is find the eigenvalues. And sometimes they're going to be really nice, and sometimes they're going to be real trash. I don't know what these are going to be because I just made this up, but I'm fine with them being whatever because we're prepared to talk about imaginary stuff. So let's find the eigenvalues. So we're going to solve the determinant of a minus lambda I equal to 0. I didn't even write down. You should be able to see what the matrix A is without doing anything here, but the matrix A is just the coefficient matrix, 3, 5, -1, 1. Make sure when you look at this, nothing's out of order, right? If someone was unkind and wrote this as x2 minus x1, you really need to make sure that the variables are in the same order so that we get the coefficients all matching up the right way. So this is going to be 3, 5, -1, 1. So then we're going to try and solve the determinant of the matrix 3 minus lambda, 5, -1, 1 minus lambda, and that should equal 0. Oh, yeah, there was something. Someone's asked about superposition. We'll talk about it in a minute here, but we'll do this for sure. So the determinant is going to be 3 minus lambda times 1 minus lambda minus -5 equal to 0. I might have lucked out and picked something nice. You'll never know. We'll find out in a second here. So let's see. Multiplying this out, you're gonna get lambda squared. Minus 3 lambda minus lambda is minus 4 lambda, and plus 5 equals 0. And you might be able to trick yourself into thinking this factors. It does not factor. There are no nice integer numbers that multiply to positive 5 and add up to negative 4. Right? You can either pick 1 and 5, those add up to 6, or negative 1 and negative 5, those add up to negative 6. So this doesn't factor, but it feels like it should. So if something doesn't factor, we still want to find the eigenvalues, we use the quadratic formula. Unless I made a mistake, right? Oh, you know what? I did make a mistake. Yeah. So this doesn't factor, but I missed something, didn't I? I missed the plus 3 here, right? I still think it's not going to factor. But I was about to make a big mistake. Be careful here. Don't be James. I mean, usually it's okay to be James, but sometimes James makes mistakes. Lambda squared minus 3 lambda minus lambda is minus 4 lambda. But then you also need the plus 3 plus 5. So this really should have been lambda squared minus 4 lambda plus 8 equal to 0. Fun fact, I know I said this last time. I think it's kind of interesting. That number there is always the opposite of the trace of the matrix. The trace in this matrix is 3 plus 1, which is 4. That number there is negative 4. That checks out. And that number there is always the determinant of the original matrix. The determinant here is 3 times 1 minus 5 times negative 1, which is 3 plus 5, which is 8. So I should have looked at them and like, oh yeah, that's not right there. But that's always true. It is always, always, always true that this equation is for a 2 by 2 matrix is always going to be lambda squared minus the trace times lambda plus the determinant equal to 0, where we use the tau symbol for trace and that symbol for the determinant. Still doesn't factor, which means you still have to use the quadratic formula. So our solutions here are going to be, this is going to be not nice, but it's good to see ones that are not nice because sometimes they're not nice. So our solution be lambda equal to negative b plus or minus the square root of negative b squared minus 4 times a times c all over 2 times a. So let's see what that gets us. I think they come out to be kind of nice imaginary numbers at least. Imaginary? Yeah, imaginary. So we get lambda equal to 4 plus or minus 16 minus 32 is negative 16 all over 2. The square root of negative 16 is 4i. You get 4 plus or minus 4i all over 2. And then divide each part by 2 to get 2 plus or minus 2i. One thing to be careful about here is not to divide the 4 by 2 and to like, I've seen people incorrectly say that this was equal to 2 plus or minus the square root of negative 16. That's not right because each of those pieces has to get divided by the 2. So we cannot do that. But just be careful. So now what? We've got the eigenvalues. Now we're going to find the eigenvectors. Yeah, the eigenvectors. I will admit perfectly, this is a place where I get a little bit like, ooh, we got to be extra careful because it's a little bit messy. In fact, I wrote myself some notes over here. Yeah, cool. All right, good. So to find the eigenvector, yeah, questions. Yes. And we'll talk about why though, because it's actually pretty easy to see why. So let's find one of the eigenvectors. So typically, right, finding eigenvectors, we're trying to solve a times the eigenvector equal to lambda times the eigenvector. And yeah, I would still do. So again, I would say as long as your eigenvalues are relatively nice, meaning you don't have gross like irrational things or even like fractions, you're probably fine. This is a relatively nice eigenvalue. Even though it's imaginary, you still have integer values for your coefficients. So I would say that this is nice enough that I would still solve it this way versus solving it this way. Whatever you like is what you like, though. Do it whichever way you like. Either way is totally fine. There are times when things get messier where this is probably preferred, though, I would say. but I would say things are not that messy here. So let's do it this way. So my matrix was, what was my matrix? Did it just disappear? Oh, there it is. 3, 5, -1, 1. So I'm trying to solve 3, 5, -1, 1 times the matrix we're trying to find, sorry, the vector that we're trying to find, equal to 2 plus 2i times x1, x2. Let's use the first row. The first row seems worse, James, but fine. So we're gonna use the first row. We're gonna get 3x1 plus 5x2 equal to 2 plus 2i times x1. That's your first row equation. And then just like any other time, we're going to kind of isolate the x's and the x1s and the x2s. So I'm going to subtract 3x1 from both sides. Yeah, I don't love the choice I've made here. I'm going to get 5x2 equal to 2x1 minus 3x1 is a -1x1. So I have a -1 plus 2i times x1. Now here's where that thing I said before about how to pick the coefficients is actually really nice. Instead of doing more work, we can say that our eigenvector is equal to x1 is 5, x2 is -1 plus 2i. It totally works. Let's look at this a slightly different way, just so that so you can see all the things. So I think there's a lot to see here. So let's look at this. Let's look at the row 2 equation instead, and look at the eigenvector we get that way, which was gonna. I'm gonna tell you right now, it's gonna look different.
Wait. How did you get that 5x2?
So this right hand side here is equal to 2x1 plus 2i times x1. And then I subtracted 3x1, and 2x1 minus 3x1 is a -1x1.
Okay.
But I still have the plus 2i x1. Basically, you have to keep the real parts and the imaginary parts kind of separate from each other.
Okay. So why don't you multiply the 2 plus 2i times x2?
Why don't I multiply the 2 plus 2i times x2?
Why don't, no.
So again, well, when I'm writing this out, I'm doing this row dotted with this column equal to this first row.
Oh, okay.
Let's look at the second row equation, and then I think it might become more clear.
So this is the first row.
Right, but here's the thing. You only need to use one of the rows to find the eigenvector. You never ever need to use both rows. Let me show you. Then maybe you'll believe me more. So let's say we use the second row instead. So use row 2. I get -x1 plus x2 equal to 2 plus 2i times x2. I'm going to do the same thing I did before. I'm going to bring all the x2s and x1s to separate sides. So I've got a 2x2. I'm going to subtract one of those x2s and get -x1 equal to 2 minus 1 is 1 plus 2i times x2. Is everyone cool with the work I've done? It's okay. If you're not, say something. I'll explain more. I'm happy to explain more. Okay. So then I'm going to do the same trick I did last time. My vector is going to be, well, x1 is going to be the coefficient of x2. And x2 is going to be the coefficient of x1. And I will fully admit, you probably are saying to yourself right now, James, those vectors look nothing alike. Oh, God, geez, okay. And you'd be right in that they're not the same. But eigenvectors don't have to be the same. They just have to be multiples of each other, right? If 1, 1 is an eigenvector, so is 2, 2. So is 3, 3. So is 20, 20. Any multiple of an eigenvector is also an eigenvector for the same eigenvalue. So the real question here is, are these eigenvectors actually multiples of each other? And the answer is, for sure they are. Let me show you. What can I multiply by -1 to get -1 plus 2i? I think it would be 1 minus 2i. So if I multiply this whole eigenvector by the scalar 1 plus 2i, no, 1 minus 2, I'm sorry, 1 minus 2i. Let's do the second component first. So -1 times 1 is -1. -1 times -2i is positive 2i. And then 1 plus 2i times 1 minus 2i, well, 1 times 1 is 1. 2i times 1 is 2i. 1 times -2i is -2i, and those cancel out. And then 2i times -2i is -4 times I squared. But I squared is -1. So you would have -4 times -1, which is positive 4. But look, that's the same as that. So either one of these choices is a perfectly good choice for the eigenvector here. Is one better than the other? I honestly can't say. I'd probably pick that one over that one because that one has a 5 in it and that one doesn't. Like, that's really, like, I'm always trying to pick the smaller numbers here, but really it doesn't matter. We might as well talk about it. So you could have done it this way, or if you don't like this, you can do it the other way. You can say, James, I really, really don't like it when you do it that way. I would much rather you said, we're going to solve a minus lambda I times v equal to 0. And be like, okay, well, a minus lambda I, so we're going to do a minus lambda I, and lambda is still 2 plus 2i. So we're going to have 3 minus 2 plus 2i, 5, -1, 1 minus 2 plus 2i, times our x1, x2 equal to 0, 0. And here you might actually more easily see why both solutions are really kind of eigenvectors. So if I rewrite this first equation, sure. I've got 3 minus 2 is 1 minus 2i, 5, -1. 1 minus 2 is -1, and then -2i. Normally, when you do it this way with like nice real eigenvalues, both the equations end up looking the same. Like you get like a 1, 2 and a 1, 2, or the same, like a multiple, like they just end up being much nicer. Here, these are still multiples of each other, because what we're getting here is 1 minus 2i times x1 equal to 5 times x2, or -1 times x1 equal to -1 minus 2i times x2. And those are literally almost the same equations that we had from the other way of doing it. We're off by a sign. We're off in the not wrong way by a sign. Not wrong way. I mean, Now I have to think about this. Really. Oh, no, that's interesting. What's going on here? There's something. Sorry, now my brain is like, what's going on? All right. Yeah, thanks. Yeah, I'm so used to doing it the other way. I apologize. Thank you so much. I was like, that seems not quite right. We're gonna be off by a sign. Yes, if we do the right thing and you say 1 minus 2i times x1 plus 5 times x2 equals, sorry, 0, then you get the same equation. Or -1 times x1 plus -1 minus 2i times x2 equal to 0. Both of those lead to the same equations we had. 5x2 equal to -1 plus 2i times x1, or -x1 equal to 1 plus 2i times x2. Pun intended here. Complex eigenvalues are complicated. They're complex, both literally and also actually when we try to do them. But here is the nice thing. It is true now that for lambda equal to 2 plus 2i, the eigenvalue was, or the eigenvector was, and let's just pick the one I said I was going to pick. I'm going to pick the second one, which was 1 plus 2i comma -1. And then for the other eigenvalue, the conjugate to minus 2i, the eigenvector is literally just every input is just its complex conjugate. So you get 1 minus 2i, comma, negative 1. And honestly, what you could actually do if you really wanted to is go back through all the work we did and just change every plus sign in front of an I to a minus sign. And if you do that, look what happens. You get a minus here. You get a plus here. You get a minus here. You get a plus here. And then doing it the right way, not over there, you get a plus here. And you get a plus here. And so that becomes a minus there. A minus there. And so here, if I'm using this one, my eigenvector, well, the x2 coordinate is -1 and the x1 coordinate is 1 minus 2i. So literally just changing all the imaginary pieces to their opposite sign changes the imaginary pieces to their opposite sign. From this equation here. So the fast way of doing this is to say, or actually I'm using this equation. The fast way of doing this is saying x2 is equal to the coefficient of x1. And x1 is equal to the coefficient of x2. But here's what's really happening. We could solve for x2 if we wanted to. And say, yeah, x2 is equal to, sure, that's probably the wrongest way to do it, but it's fine. -1 divided by 1 plus 2i times x1. And the idea is, what are you going to pick for x1? Well, I'm going to pick, I can't pick 0. Remember, you can't pick 0, 0. I'm going to pick x1 equal to 1 plus 2i. And if x1 is 1 plus 2i, then 1 plus 2i times -1 over 1 plus 2i gives me an x2 of -1. But really, what we're doing here is just saying you can pick anything you want. So pick the easy choice. Go back over here and say, okay, well, if x1 is that coefficient, then x2 has to be that coefficient. It's easier seen maybe if I said I was solving something like, if I got to a place where I was solving 3x1 equal to -5x2, I know that my vector, which is x1, x2, one plausible choice is x1 equal to -5, x2 equal to +3. Because if I plug in a -5 there and a +3 there, are things equal to each other? For sure. And I pick 0, 0? I surely didn't. You could have made other choices, right? Another typical choice, although not preferred, but another way to go here is to solve for x2. Say x2 is equal to -3/5 times x1, and then pick x1 equal to 1 and x2 equal to -3/5. Is this also an eigenvector of whatever this matrix that this eigenvalue would have came from is? Yeah, because these are for sure multiples of each other. But this is the easier choice. This is the preferred choice because we don't have any fractions. So that's what we're usually doing when we get to this stage here. Is just like, oh yeah, let x2 be that number, let x1 be that number, and you're good to go. It works every time. It's less nice when the numbers are not integers, but it still works every time. Oh, we were going to write the solution to this thing. We got 5 minutes ish. Okay. The solution here, I will fully admit, is a little bit wonky. So, and I'm actually going to look at the notes here so I don't blow it. Yeah, it's super weird. I'm really not a fan. Okay, so what do we do first? Oh, no. Are those all my notes, James? Good job. What do we do first? I have forgotten. It's been so long. I think what we're supposed to do is we're supposed to write our eigenvector. Yeah. Yeah, let me not just try and make it up and confuse you all. Let's just say some other things and we'll come back to this because I will say the solving of a system with complex eigenvalues is not impossible, but often not the focus here. So let's talk more about what we've got. So our system, which was represented by the matrix 5, 3, was it 1, -1? Yeah, oh, sorry, 3, 5. -1, 1. We're setting that equal to, that's right, that's our dx1 dt. So our eigenvalues ended up being, sorry, I forgot what they were, 2 plus or minus 2i, yeah. Sorry, I've got work everywhere. We're 2 plus or minus 2i with eigenvectors that were 1 plus 2i negative 1 or 1 minus 2i negative 1. So yeah. Oh, sorry, yeah. So the idea here is just like before, our solution is something of the nature c1 e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2. And although we're not going to write that down exactly right now, the thing that comes into play here is that when I look at specifically e to the 2 plus 2i, looking at that one first for a second, e to the 2 plus 2i I'm going to break up into two pieces. It's going to be e squared times e to the 2i. And then there's this formula for e to an imaginary coefficient, which is kind of weird. It says that e to the 2i, or e to the something times I, is equal to, oh, sorry, I lost a tiny little piece here. Gosh, today's been interesting. I forgot the t, right? There's a t there. So there should be a 2t there and a 2it there. Sorry about that. This is going to equal e to the 2t times e to the I times 2t. And then this part here is going to be, this is where things are kind of funky. It's going to be cosine of 2t plus I times sine of 2t. Where does that come from? You guys like, right? Does that seem at all reasonable to you? Probably not. You know what? That's probably the best use of our last couple minutes here. So we'll talk about why this is true. And then on Thursday, we'll delve more into all of this, but not too much. So why is this the case? Well, let me show you some things. All right. Yeah, we got enough time. So I is the square root of negative 1. I squared is negative 1. I cubed is negative 1 times I. I to the fourth is negative 1 times negative 1, which is 1. And then you kind of repeat, you finish the cycle. You get I to the fifth, you're back where you started. I to the fifth is I to the fourth times I, which is just I, and so on and so on and so on. Okay, I don't remember if this is something you've seen or not, but I'm going to tell it to you anyway. There is a way of writing sine and cosine as a Taylor polynomial, or a Maclaurin series. We can write sine of theta as theta minus theta cubed over 3 plus 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial forever and ever and ever. And similarly, cosine of theta can be written as 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, and so on and so on and so on. And just because it's worth seeing here, e to the theta is equal to 1 plus theta squared over 2 factorial plus theta cubed over 3 factorial plus theta to the 4th over 4 factorial, and so on and so on and so on. So if you haven't seen this before, I'm happy to talk about some other time, but this is where things are coming from. So now I know we're out of time, but bear with me for like just a couple more minutes. I promise you it's worth the wait. So e to the I theta. So I'm just going to replace every theta with an I times theta, and look what I'm going to get. I'm going to get 1 plus I times theta plus I squared times theta squared over 2 factorial plus I cubed times theta cubed over 3 factorial plus I to the 4th over theta times theta to the 4th over 4 factorial. We'll write one more term. Okay, but now look, all of the terms that have an I to an even power are not going to be imaginary. I squared is -1. I to the 4th is +1. I to the 6th is -1. I squared is positive. I to the 8th. So I'm going to break that up as 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial, because I to the 4th is positive, minus theta to the 6th over 6 factorial, and so on and so on and so on. Plus, from all the other terms with odd powers of I, I'm going to factor out an I. So when I do, I'm left with theta here. I'm left with an I squared, which is -1 times theta cubed over 3 factorial. Plus, if I factor out an I from I to the 5th, I'm left with an I to the 4th, which is +1 times theta to the 5th over 5 factorial. And you can see the alternating behavior. But look, that is exactly cosine of theta. That is exactly sine of theta. So this really does equal cosine of theta plus I times sine of theta. It's one of the most famous mathematical formulas probably known to man. It actually is the basis for the equation you might be aware of, which is that e to the I times pi is equal to cosine of pi plus I times sine of pi. Cosine of pi is -1. Sine of pi is 0. And people often write this as e to the I pi equal to 0 minus 1. The equation involving the 5 most important numbers in math, for lack of a better term. So kind of a cool equation, but more importantly, this equation is where that other thing we said is coming from, where you're actually getting this e to the 2 plus 2i and breaking it up into these 2 pieces. And then next time we'll talk about how the cosine sine part actually is what leads to the oscillation of your solution, which leads to your solution not being a sink or a spiral or a source, but a spiral. The oscillating of sine and cosine is what leads to your spiral behavior in your stable spiral or your unstable spiral. Okay, I'll stop talking. It's 1:23.